Thank you. Yeah, thanks for inviting me to this conference. All the talks were really nice. Right, so I'm going to talk about Eisenstein series. So usually in the Langlands correspondence, you're interested in studying some representations of some connected reductive group, usually some kind of infinite dimensional representations. And Eisenstein series and sort of all the different incarnations of the Langlands correspondence is some kind of way of adding some kind of inductive structure to that classification problem. In particular, reducing it to sort of some, so in particular, it allows you to build representations of a connected reductive group G from representations of its Levy subgroups, so smaller reductive groups sitting inside. And usually a lot of the interesting analysis around this infinite dimensional representation theory is contained in this theory of Eisenstein series. Right, so let me just start. So I'm going to take G, connected inductive group over, let's just say, the p-adic numbers. I'm going to take T to be some parabolic subgroup sitting inside there, parabolic, which has a Levy decomposition into its reductive part, its Levy quotient, and its unipotent radical, which we'll note by U. And then for coefficients, I'll take lambda to be at least for now, a Z1 over P algebra. And inside lambda, let me fix a square root P. So then, given this square root, I can consider first what's known as the modulus character. So it's going to be some character M of QP mapping to the units and lambda star, which is basically defined in terms of the roots coming from this unipotent radical and the norm character on QP. And so in particular, if I fix some square root of P, then this will also determine for me some square root of the modulus character. Right, so the main object of study here is going to be what we know as E, GQP. And this is going to be the derived category in a suitable sense of smooth lambda representations. And so in particular, you can just think of it as well, some possibly infinite dimensional lambda module P together with an action of the p-adic points of this reductive group GQP reflected by some homomorphism phi. So I can write the limit over its so in the local Langlands correspondence, the main object of study is basically going to be this derived category here. So we want to have this tool for building representations from smaller Levy subgroups. And so in this context, that's given by the operation of parabolic induction. In particular, we have all the functor. Not from smooth representation for Levy, smooth representation group. And what this will do, if I have some smooth representation and here, then it's going to map it to the following GQP representation. This could be given by the space of functions on G of QP towards n. So for here, maybe I'm assuming this is just concentrated in one homological degree. Well, such that n is locally constant and smooth. So it's invariant under some compact open subgroup. And it satisfies the following transformation property. So So if I were to take an element in my parabolic, and I want, well, I just get the function back again, together with its scaling, I m, and then I also need to add this sort of fudge factor given by the modulus character. Yeah, if you don't know what this is, you can just kind of ignore it. Basically, it's going to be necessary because once you start taking duals of various things, this character is just sort of going to naturally appear. So adding the square root here just makes sure that doesn't happen. Right. And well, I think an example of this was already discussed. In particular, a nice example you could do is you could just take the case where m is the torus, and you could take this representation to just be the inverse of this modulus character. And so in particular, this would just be invariant functions under this parabolic. And so you can think of it as functions of the flag variety. And then, well, those functions of the flag variety, there's a subspace given by the constant functions, which will just be the trivial representation. And then the quotient is what's known as the Steinberg representation. So this appeared, I think, in Jared's talk when he was describing the p-adic pro-étoile cohomology of the Drinfeld upper half. Right. So this functor over here, it comes in some kind of adjoint pair. So there exists an adjunction and well, okay, you can give a similar concrete definition of this by basically just quoting out by the space of co-invariant vectors. And so the fact that this adjunction exists, so this is some kind of induction and this is some kind of restriction, this is just some example of what is known as Frobenius reciprocity.
Function is left at point in each one.
Oh, okay, sorry. Oh, this is the left.
Can I ask you which method we use for this?
It would say that restrictions is left for the duct.
I say restriction is like sorry, you had a question?
Just a graphical one. Which method do you use for the left one?
For the letter what?
For the left one.
Oh, this is an R.
Ah, I see. Okay.
Yeah, and yeah, this is what's known often as the jumping.
Okay.
Right, so we want to understand how these kinds of functors interact with various notions of finiteness, because we're basically studying sort of infinite dimensional representations, and so such notions of finiteness are going to be important for us. And it's very useful to think of notions of finiteness as coming from sort of kinds of duality. So maybe as a test example, you have just a set of vector spaces, and you want to sort out what are just the finite dimensional vector spaces inside there. And they're just going to be the ones that are isomorphic to their double dual. In particular, this category comes equipped with certain kinds of duality. So there's sort of two kinds of duality in this category. And if I have some object A inside here, well, that's going to map to, well, first we have what's known as the smooth dual. So this behaves like very similar to a usual notion of duality. Essentially what you do is you just take A, well, constant object. So in other words, all you're looking at is sort of functionals on these representations, which will have some natural GPP action. And then maybe you also pass to smooth vectors. So you replace it by its co-limit by these open compacts. This is what's known as the smooth dual, and maybe I'll abbreviate this as follows. But then there's another kind of duality. And this is homological duality. And what this does is so we have a smooth representation, but then we can view it as a module under space of compactly supported smooth functions on G of QP. This is the smooth algebra. And we can take the Arham module from A towards the Heckel. So this is some kind of regular representation. So it has a left action and a right action by G of QP. And so when you take this Arham, you're going to forget one of those actions, but there'll still be some leftover action. And so this will have some structure of a G of QP representation. And this is what's known as Bernstein's homological duality. And I don't have time to really fully go into this, but as you can imagine, that because this is some kind of regular representation, and so by analogy with the algebraic, with the Peter-Well theorem, it's sort of going to see all the different smooth representations. This is going to interact in an extremely interesting way with this derived category. So this is maybe the more representation theoretically rich of these two dualities. So we have these two dualities, so they're going to give rise to certain notions of finiteness. So we can ask, what are the subcategories where this induces an equivalence?
So you write in the superscript at the top?
Yeah.
Because they're both contrary.
Yeah, it's a contravariant. Right. The homological, or let's say maybe D smooth, respectively to D homological, will induce an anti-equivalence on, well, the subcategory which I'll denote as D admissible on a lambda. And this will denote, this homological duality will induce an equivalence on, well, subcategory that I'll denote as dg2p lambda omega. So what is this thing? Well, this is basically just going to be the set of objects A such that, well, its invariance AK, compact open pro P subgroup. I'm saying pro P to get rid of possible higher invariance is a perfect complex. So in particular, I mean, this is easy to believe because this is going to behave a lot like the usual notion of duality on vector spaces. And so this is going to reduce to this fact that I mentioned before, that you can single out the finite dimensional vector spaces as the ones that are isomorphic to their double dual. Well, at least when lambda is a case. And so this thing over here, well, this is going to be the set of compact objects. So this is just meant in sort of the abstract categorical sense as an object such that when you take harm from it, it's going to commute with colimits. So it turns out that this category, so dg2p lambda, is actually compactly generated. In particular, you can write every object inside here as a colimit of objects inside here. And you can actually be very explicit about what these what these compact objects are generated by. So this it's going to be generated by well, just sort of certain compact inductions from K to G of the trivial representation of K, where K is just some compact properties. So it's maybe good to note that these really generally give rise to different definitions of finiteness. So in particular, if you took the dual or the smooth dual of this thing, it's pretty easy to see that this is going to have uncountable dimension. So it has no chance of being admissible. But maybe as an aside, if you were to take lambda of rational coefficients, and you were to consider the intersection of these admissible complexes with a set of compact objects, then by a non-trivial result, no matter how, this is going to be the same as sort of the derived category of finite length representation. So basically the key point here is that when lambda has rational coefficients, the category of smooth representations will have bounded homological dimension. So finite length here just means that, well, the complex has finitely many cohomology sheaves, and each cohomology sheaf has a finite filtration whose graded pieces will be smooth, irreducible representation. So this shows you that this is really capturing sort of all the nice notions of finiteness you could hope for in this category. Right. So we want to understand how this parabolic induction functor, this Jacquet module, interact with these notions of finiteness. So this is captured by the following theorem, which was first, I think, with C coefficients was proven by Bernstein. And then I think the torsion coefficients was seriously treated by Vigneras. And then, well, actually in this torsion case, this has actually a very long history. But actually was very recently resolved in work of Gotthelm, Rindhoek, and Moss. So in this full generality of lambda as a Z1 over P algebra, actually using techniques in the partials over the Langlands correspondence. So what's the theorem? So first, there exists a series of junctions. So we can first start with our Jacquet module, and then this has a left adjoint given by Linus reciprocity. To IPG. And then, well, it actually turns out that this emits a further right adjoint. So this is what's known as second adjointness. So this will be given by the Jacquet module of P bar. So P bar of the opposite. And then, well, you can just keep going, right? So the IPG, and you'll be back at RPG. And then this will continue infinitely cyclical fashion in both directions. Then result B is that, well, this functor RPG and IPG preserve compact and or admissible complexes. And then C has to do with how these functors interact with duality. So there exists natural isomorphisms from, well, so if you take the cohomological dual of the parabolic induction, it's going to intertwine this with the parabolic induction with respect to the opposite parabolic. And if you look at these Jacquet modules, well, then smooth duality is going to intertwine this with the opposite. But I mean, these results are all very much connected to each other. So let me just briefly remark about that.
I know it's not the main point, but I saw it because his name is often forgotten. Somehow in the admissible case, the second statement is due to Hansen and region.
Oh, the second?
I only like part of the
preservation of admissible.
And the last line for C.
On the last line first. Oh, okay, so for this isomorphism.
Yeah, in the admissible case, just because Castleman.
Oh no, I'm happy to include.
Can you repeat the comment for the?
Oh, so apparently this observation that this smooth duality will interchange the Jacquet functors is due to Castleman, so this isomorphism.
For admissible rest.
For admissible representations. Yeah, so let me just briefly remark that all these results are sort of connected to each other. So remark that this actually A is just going to basically imply B. And this has to do with the fact that, well, okay. I mean, actually the existence of this series of infinite adjoints is going to guarantee that all these functors are going to preserve compact objects. This is sometimes known, so like if you want a functor preserve compact objects, it's enough to know that it admits a right adjoint, and then that right adjoint admits another right adjoint. So this is sometimes called Neumann's criterion, the Neumann's theorem. But you can kind of see why they would have something to do with each other because, well, checking something compact is saying that on from it commutes with colimits. So then if you have a left adjoint functor, you can move the right adjoint onto the colimit. And then if that right adjoint also happens to be a left adjoint again, well, then it will commute with that colimit. That at least allows you to see that these two things will be related to each other. And then for the admissible case, you can note that actually if you take Archon from one of these compact generators, A, it's actually just the same as taking invariance under K. So in particular, saying your admissible is the same as saying Archon from all the compact generators is a perfect complex. And this will allow you to transfer questions about the preservation of admissibility to the preservation of compact by passing the adjoint functors. Right, and well, actually, A is also going to imply C, but this is maybe a little bit more subtle. So you can look at well, the discussion around page 100 of Bernstein's lecture notes. Yeah, sorry. The only explanation I could give would use 6 functors.
A and C are even logically what the precise.
Yeah, A and C are actually. And these two isomorphisms are actually equivalent to each other too. Yeah, I just don't have time to go into this. Right. So this is basically the main theorem that we're interested in, at least in this category of smooth representations. And so now we want to understand the incarnation of this in the geometrization of the local Langlands correspondence to the Fargues-Fontaine. But before we do that, maybe are there just any questions on this discussion here? No questions? Okay. All right. All right, we want to study this in sort of a geometric incarnation of the local Langlands correspondence. So what are we interested in there? So we consider bun G to be the moduli stack, moduli B stack of G bundles on the Fargues-Fontaine curve. So okay, this requires a lot of p-adic Hodge theory and perfectoid spaces to even define, but it actually turns out that the output of this construction is fairly concrete. In particular, we can just consider this stack, whatever it is, and look at its underlying topological space. So this is a set. So in other words, the set of isomorphism classes of G bundles on this curve will be the same as what's known as the Cotlet set of G. So this is some, well, object that's, well, appears a lot in the theory of Schemler varieties and has some very explicit combinatorial description in terms of, well, certain polygons with rational slopes. Kind of think of as Fargues-Fontaine slopes. In any case, if we're given some element B inside here, well, then this will define for us a locally closed substack inside bun G of B. But topologically, this will be a point, but of course that point could have automorphisms. This will be the point, and then quotient out by some group of automorphisms, JB. For this JB, there's going to be some semi-direct product, some p-adic group together with some part that I'll mostly ignore. So this is just going to be ell-adically contractible. So I'm also going to now fix the problem L this time. And this over here is just some p-adic group. So in particular, this is some inner form of a Levy that you could attach to G. Right. So what are we interested in studying? So I'm just now going to work with FL bar coefficients to avoid some kind of existential issues. So we're interested in studying, so what I'll denote as D on G will be the derived category of a tall FL bar sheaves on this space. So I'm going to omit the coefficient system often just for simplicity. And so by the fact that you have this decomposition into these locally closed subsets, by excision, this has a semi-orthogonal decomposition. Into derived category of smooth representations of this p-adic group. Because essentially this unipotent part isn't going to contribute, and you're just going to see the classifying stack of this. So you can identify sheaves on it with just this category of smooth reps. Right, so I mean, you can just think of a sheaf on Bungie as just some collection of smooth representations of varying inner forms together with some gluing datum across all the different strata. Right. So in particular, if we just consider, well, the Schrieg put forward from the neutral strata, then this will just realize the category of smooth representations that we were studying before as a subspace, or as a full subcategory of sheaves on Bungie. Right.
So that's just, maybe for non-experts, maybe it's worth saying this B of G has like some canonical element that you're calling fold one.
Oh yeah, sorry. Yeah, let me just say that this corresponds to the trivial G bundle. So this will just correspond to the locus given by the trivial. Right. Okay, so we want to understand now some notions of finiteness on this category, just like we did over here. So again, we want to think of this as coming from some different kinds of duality. In particular, we can consider the following functors: B bared and BTC, mapping from E on G to E on G off. So what are these things? Maybe I'll for I'll keep that up there. Right. So so this variable. So let's consider right pi for the map from Bungie to the point. So this is just going to send an object A to its variate dual. So this will be upper streak bar. But it actually turns out that the dualizing complex on this is just isomorphic to FL bar again. So this is actually an incarnation of the fact that the group G is unimodular. So in particular, the module of Haar measures is going to show up in the dualizing complexes of these classifying stacks. And then this relationship will actually persist over all of Bungie. And while this Bernstein-Zelvinsky duality, this is a little bit weirder. So this is characterized by some Yoneda property. So in particular, if you took Arham of PBZA into NEB, and this will satisfy the property, this is isomorphic to the street push forward for a tensor product of A and B.
Sorry, what's the meaning of the letter pi? Because art pi, which.
The letter R?
No, the next letter pi.
Pi is the
sorry. Pi is just a map from Bungie to the point.
So at the beginning was lambda, now it's FL bar. Is this for simplicity because you want to work out things or?
Yeah. It's just like if in general, I would have to replace this category of sheaves by something a lot weirder, and I just don't want to get into that right
Linus, can I make a tiny notational comment? I think you might want to distinguish internal and external R humps. So those two R humps are meant to be of different nature.
Yeah. Right. So this is going to be some.
Okay. Like you can make your H curly on the first one or something.
Sorry, my H?
R hump on the B there, it should be like a curly H in the hump.
Yeah.
Or underline, whatever you want.
Yeah, I was a bit sloppy about this.
But wait, is it essential that you work with FL bar? It's allocated to vectors.
Well, so the thing is that like you're gonna have to be more careful about how you define this derived category of tall sheaves, because if you work with something like ZL, this is not going to capture the set of all smooth representations.
Yeah, but suppose not CL, but C mod L to the power of n with fixed.
Yeah. Then you could just do.
Then there's no difference.
Right. Yeah.
So if you wish, replace FL bar by WN.
Yeah, exactly. You could replace this by any adsorption algebra.
In the paper, we allow any lambda.
Right. Okay. So actually, I mean, this looks super weird. Like, what does this have to do with what I wrote down before? So let me just remark. So if you restrict to this neutral strata, so on G1, and we'll then set so this B just equal to the smooth Heck algebra, then the right-hand side of we call 1, called dagger, right-hand side of dagger will just be A. So as will be the underlying complex of A. So in particular, R hump to this Heck algebra is undoing whatever this Bernstein-Zelvinsky duality did, and because this is an involution, that means that this property is a good characterization of it. And to see why that's true, you can describe the smooth Heck algebra as the street push forward of the constant sheaf along the map from the point to this classifying stack, and then you take homology again. So in particular, the opposite of this is just going to be the constant sheaf again. We combine that observation with projection formula to get this claim.
So again, on the more familiar category, so does this duality include anything on the more familiar category at this? Representations of G of.
Okay. So this Bernstein-Zelvinsky, or the admissible duality? Yeah, so this will induce, by what I was trying to say over here, this will induce the cohomological duality on the neutral strata.
Can you write the formula, just for clarity? It's not long.
So, and so in particular, right, so the Bernstein-Zelvinsky duality push forward would be the same, push forward, and then you apply homological duality. And a similar thing will also be true. Okay, I have to be a little bit careful, but I mean, this Verdier duality will essentially intertwine smooth duality on the neutral strata. We'll change the streak to a star, of course.
Is there a formula for DBZ, just as there was a formula for DCO?
Well, I mean, this is a formula, right? But you're not content with this.
But you have to. I mean, I guess it requires showing that it exists, right?
Yeah, I mean, I mean, honestly, what DBZ does is actually very mysterious. I mean, even in just regular smooth representations. So you can write down an explicit set of compact generators, and it's not really going to do too much to these compact generators. And then sort of it's defined just abstractly by sort of taking co-limits. these objects. But I mean, in some sense, the whole problem is to kind of figure out what this thing is. So
there's a version of unusual geometric Langlands, and they call it miraculous duality. That's the technical term for it.
Right, yeah. So this is analogous to this miraculous duality.
And you mean the miraculous duality which appears in the work by Finiteness?
Yeah, exactly. Right.
So what does it do to objects that are like they come from a particular B, and on that B they're like induced from compact?
All right. Yeah. I mean, so if you have this like you push forward pi, and you hit it with like Bernstein-Levinsky duality, and this will be the same as some weird sharp push forward of homological dual of pi. So abstractly, this is a left adjoint to restriction, but actually you can explicitly describe this thing in terms of geometric Eisenstein series. So in terms of these magical charts at B. But what these charts are doing is actually extremely mysterious. Yeah. So like what the other stocks of this are actually extremely interesting.
Okay. So I think you just said it, but so the IB sharp object won't be living just a P.
No. So this will be supported on all the elements less than. And in fact, okay, maybe it's worth remarking this here, is that like if you know something about local Langlands, you know that there are like some supercuspidal representations that occur in packets that don't have supercuspidal representations. And in some sense, the only way you can access them in the categorical conjecture is by taking these weird kind of push forwards and then restricting to the neutral strata. These kind of supercuspidal representations will miraculously appear in these stocks. So this is an incredibly rich thing. Well, it uses your work actually, and you prove that using HKW. What was I doing? All right. So okay. Right. So again, these notions of duality will give rise to certain notions of finiteness. There, respectively, BBC will induce equivalence on. Well, okay, so first will be what I'll call DULA1G. And the second one, well, this is just going to be, again, the set of compact objects. Okay, this is again so this actually ends up being a compactly generated category. Just proven in Fargues-Fontaine there along, well, spiritually very similar lines to the work of Drinfeld and Gates-Corey in the function field case. But actually, you can write down explicitly what it means to be compact. So in other words, it has, so maybe I say it's supported on finitely many B, and has compact stocks. So it's compact in the sense I mentioned it. Right. And so this thing over here, well, this would be equivalent to having has admissible stocks. But I wrote this bizarre word here, which is ULA. So that has some meaning in classical constructible sheaves over schemes, and it has some analogous meanings here, but this is really going to be the set of sheaves which are ULA over the point. So with respect to this map pi over here. And this is really bizarre because usually being ULA is some condition about like, well, if I specialize on the source, on the target, then, well, the sheaf needs to be constant along the pre-images of those specializations. But if the target is just a point, that doesn't really mean anything. So usually it's just a completely trivial condition over the point. But let me maybe make some brief remark about what the definition of this is. So if you just have like some reasonable map of spaces, say some reasonable map, in the sense that all 6 operations exist, you consider an object A in the derived category of X. Well, you can reinterpret actually this derived category as being some kind of homomorphisms from S to X in some category of correspondences. So in other words, like it's like the usual category of correspondences, but the maps are not given by cycles in the product of the things, but rather actually just sheaves on the product. The fiber product of X and S over S is just X. And so then A being what we say FULA is actually equivalent to A as a left adjoint in CNs. Right. Okay, you don't really have to understand this, but this is a definition that will work in both the scheme context and this context. And in particular, one thing this definition does is you explain the fact that, okay, well, let me say actually, this left adjoint actually has to be the Verrier dual of A. In particular, like there's a co-unit and a unit map, and one of those maps is basically going to be given by the evaluation map between A and its Verrier dual towards the dualizing context of the adjoints. And so in particular, you have A being FULA, well, then you can exploit the fact that this correspondence category is isomorphic to its opposite. Because like in the correspondence category, you can just switch the role of the 2 factors, right? Because it's just going to be sheaves on some fiber. The morphisms are just going to be given by sheaves on some fiber product. And this will actually imply for you that dxa is FULA. And actually, then again, so it's going to have a left adjoint, which is again going to be given by dxs A. But then that left adjoint came from sort of the left adjoint over here, which was this A. And so in particular, it's going to imply actually that the sheaf is reflexive. In particular, this symmetry of the correspondence category makes sure that this notion always gives rise to some kind of reflexivity of your sheaves.
So,
yeah.
I didn't understand this. Can you say this word? So, so first of all, there is a kind of very formal categorical definition of
right.
Second, in the familiar world of let's say knowledge, when you have a morphism from to a point, then ULA is automatic.
Right.
It's constructible.
Yeah, that's
it's constructed. It's equivalent to be constructible. Are you saying that this now here it is not automatic? Are you saying that this ULA is a kind of replacement for constructibility?
Yes, that's
Can you
kind of
repeat the
true.
question for you?
I don't know what your question was.
Well,
Is ULA a replacement for?
Is ULA a replacement for constructible? Yes, that's how I think about it. But I mean, it really behaves like a lot differently.
So it's a kind of replacement.
It's a kind of replacement.
There may be replacement in some
right.
respects. Some intrinsic finiteness.
Yeah, in that it isolates some nice category where Verrier duality will induce an equivalence, which would usually be played by the role of constructible sheaves. But in this rigid context, constructible sheaves are going to behave a lot differently. I mean, essentially due to the difference in the notions of quasi-compactness and rigid geometry and scheme theory. And also these sheaves over here, they all have infinite dimensional stalks, so they're extremely far away from being constructible in any reasonable sense.
So it's a kind of constructibility.
Yeah, exactly. Right. So in particular, So I mean, in particular, if you have some A, this ULA on G, well, then it will be reflexive. So it will be reflexive with respect to duality. So in particular, that's going to imply that J1 over star of A is reflexive with respect to smooth duality. Because this upper star is going to intertwine smooth duality and Vernier duality. And so in particular, because we're working with coefficients in a field, that's actually just going to imply that J1 star A is admissible. So using this fact about infinite dimensional vector spaces that I mentioned at the beginning. So in particular, we see actually that the inclusion of DULA fun G inside T on G is strict. So this condition of being ULA over a point really actually captures something interesting. And let me maybe just make a remark that this is a paradigm that naturally appears in rigid geometry, which is naturally occurring sheaves. Sheaves in rigid geometry are not reflexive. And I just bring this up because this is like really a really big deal. So this really causes a lot of problems. Particularly, like you always know by projection formula that if you took the dual of a Schritt push forward, you get a star push forward. But you don't necessarily know. Usually, if you wanted to show that the Vernier dual of a star push forward was a Schritt push forward, you'd use that all the 6 operations preserve constructible sheaves, and constructible sheaves are reflexive. But as I just demonstrated, that's false here. So anytime you're thinking about things like Hermer sheaves in this context, or you want to take Vernier duals of star push forwards, you really need to show some kind of ULA thing. So this actually came up at the end of Mingja's talk yesterday. So one of the reasons constructing this kind of IC complex is hard is precisely because of this issue. So you can kind of construct this thing, but you have to work very hard to show it's Vernier self-dual. Okay, well, actually, what am I doing? Okay, so now that I went on some long explanation of these like varying notions of finiteness, let me now talk about the analog of parabolic induction. The remaining 10 minutes, I guess. Right. So this is going to be captured by what's known as geometric Eisenstein. So what we do is we consider the moduli stack bun P. So if G were GLN, this would be parametrizing flags of vector bundles such that the graded pieces are vector bundles. And so we have a map, known as P, mapping to bun G, which remembers the vector bundle that the flag is on. And then we have a map to bun N, which remembers the graded piece. When we call this. So then we define, well, the Eisenstein functor, ISP streak, to be given by taking just streak push forward, recomposed with the star pullback, and then I'm going to tensor by something very mysterious, called IC bun B. So let me just say IC bun B is an explicit sheaf given by pulling back the modulus character. Modulus character.
Sorry, I don't see what is it in there. That's the E in the right hand side of the
Sorry, let me just, I had the P's in my notes. So
Yeah, but P is fixed for now.
Yeah,
So
P will
we
just
don't
be
have
fixed.
to-
Right. Yeah. Back to the modulus character viewed as a sheaf on Bun N abelian eyes. So this will just be some disjoint union of the classifying stacks, and the modulus character will factor through this abelianization. So it defines a sheaf on here, and then you can pull it back to Bun P and then give it various shifts. And that's what the definition of this is. And then it's a theorem, which is due to myself and Naoki, that the sheaf IC Bun P is very aself-equal. So in particular, I mean, this is going to be actually some homologically smooth map. This isn't too hard to show, and this will be some homologically smooth space. So as we saw before, by the fact that dualizing the sheaf was the constant sheaf, so this will be homologically smooth. But all that tells you is that the dualizing complex sort of locally looks like a shift of the constant sheaf by some dimension. And what you really have to do here is you have to explicitly determine what that dualizing complex is, and it turns out to be given by this modulus character. So in particular, yeah, that's what's going to imply this self-control. Right. So in particular, actually, so what's the Jacquet functor? Well, we might think about the Jacquet functor as just passing to some adjoint. So this is given by a lower shriek, and so it has a natural right adjoint given by the upper shriek. This is going to define a right adjoint which I'll denote as CTP lower star. But as I mentioned before, the Jacquet functor is sort of naturally a left adjoint. And so this is not what we want to see. So instead, we can consider this times P star, where I take the star push forward. This. And then, well, okay, the lower star is going to have a natural left adjoint. So this is going to define for us the functor CTP per shriek, which will be a left adjoint. So what does this have to do with what I wrote down before? So let me do an example.
So what is the formula for this CT? Is it the formula for ice or for?
I mean, it will be given by upper star.
Yes. So this is how you explain. This is how you the motivation of the formula. But can you just write the formula?
Okay. So this one will be given by PP upper star, and then you're going to have to consider by the inverse of this invertible sheaf, and then you take the QP. Is the inverse correct? That's correct. Yeah.
Wait, no, sorry, there's no inverse.
Okay, there's no inverse on this one.
That's correct.
Yeah, so you have to use again this theorem to think through what he's left out.
You rewrite the inner thing as Q upper shriek tensored with the inverse of IC, and then you can have the adjoincies.
Right. Yeah. Thanks. So in particular, we can just look at the locus in Bun N given by the trivial M bundle. So again, this is just going to be some classifying stack like this. And then we could take the pre-image along this map. And so in other words, what we're looking at is like filtration such that the graded pieces are the trivial vector bundle. But it's pretty easy to see by Harder-Riemann considerations that every such filtration is going to be split, and the resulting G bundle is going to be the trivial G bundle. So in particular, this is just going to be, again, the classifying stack of star mod P of QP. And then this map is going to degenerate into star P of QP, followed by the inclusion 1G into 5G. Right, so now if you compute, well, i's p question mark and free for star, then what are you going to see? Well, I mean, you're going to take some representation here, then you're going to pull it back, which is going to correspond to inflating it to star mod p of qp, and then you take a trig push forward. And that's going to be the same as looking at compactly supported functions on the flag variety, or g of qp, which transform under p of qp via this inflated character. And so you can check that this will just be J1, J1 and trig precomposed with this would just be the same as G1G question mark precomposed with IPG. And let me make a remark that it's actually very easy to see this theorem of Naoki on this classifying stack, because again, as I mentioned, the dualizing complex on these classifying stacks is given by the module par measures, which by definition will be related to the modulus. And so the real content of this theorem is to see that on the other connected components where the filtrations will be non-split, and you'll start seeing like things like Banach-Holmes spaces, that the norm character still shows up. Essentially because geometric Frobenius will act via the scaling by p action on these Banach-Holmes spaces. Right. So in particular, okay. Right, if we pass to right and left adjoints, we're going to see that CTP star composed. Okay, wait, which one?
You have 2 minutes, by the way.
I have 2 minutes. Well, I'm going to state the theorem in a minute.
Okay, that's close.
That was the backup plan. So, right, so you can identify this just by passing the adjoints that this is just the same as J1G for star precomposed to the Jacquet functor. So this is just going to fall from Frobenius reciprocity. But then this other functor, this right adjoint thing, or C2P star, is going to be isomorphic. Now again to J1 G over star, but now you're going to see the Jacquet module. So this is going to use this second adjointness. Right, so with this in mind, we can now state the main theorem. So only took an hour to do it. But right, so the main theorem is that sort of the analogues of the results I wrote at the beginning are true. So let me say put asterisks for the following. So up to restricting to finite and many connected components to many connected components. So first part of the theorem is that Einstein shriek preserves compact and ULA objects. Again, for the ULA, I put the asterisk. And then B, so this Einstein start sends compact objects, these compacts, to sheaves with compact stocks with compact stocks. So in particular, if you took like the star push forward of this induction, which was realizing this trivial and Steinberg representation, that would be supported on infinitely many Fargues-Fontaine strata, which is sort of reflecting the fact that the trivial representation is non-tempered. So it can't be supported on finitely many strata, but the next best thing is true, that it still has compact stocks, and it preserves ULA objects. Again, the asterisk. I mean, otherwise the theorem will be false for silly reasons.
Did bun G become bun N at some point?
Did
There's three buns moving around.
bun G become bun N?
Well, there's an. It looks like it says bun N up there.
Sorry, yeah, this is bun N.
So G has become GL. Oh, I'm sorry. Oh,
Yeah, I'm just saying. Yeah, I'm just saying you need to restrict this functor to finite anything. And then C is that so there exists isomorphisms. So again, between this right adjoint and this left adjoint, after taking opposite parabolics, and again you're going to get that Verdier duality intertwines CTP street with CTP star. Verdier duality. And then and this VZ duality will interchange this ISP streak with ISP bar streak. Bernstein-Zelvinsky dual. And let me maybe just make one remark about what this is good for. So okay, if you take, for example, like this natural push forward I was mentioning before, so that has this very interesting structure. So let's say this is like a smoothly reducible rep. Then because this is basically the Bernstein-Zelvinsky dual of a compact object, so this will be compact. But because you can realize this also as an Eisenstein series, and this Eisenstein series will preserve ULA objects, we'll also have, we'll have compact and admissible stalks. And so in particular, if you were to work with rational coefficients, that would imply actually that this functor where you take this push forward and then restrict to another strata sends finite length representations to finite length representation. And this means that it induces a well-defined map on the Burgundy group. And and once you have these Burgundy groups, then you can start making continuity arguments, and these kinds of things are very powerful for studying the cohomology of Schmorg. So yeah, that's just one thing this is useful for. Right. Okay, yeah, that's it. Sorry.
Good. Right. Could you comment on how these Eisenstein series functors relate to some of the structures we expect to have? For instance, if you took the Fargues sheaf on M and used ISP shriek, would you get a Fargues sheaf?
Yeah, so I
repeat that part.
Oh, sorry. Yeah. So if you were to take Fargues eigensheaf on the Levy and then you were to apply ISP shriek, would you get an eigensheaf for the group G? And so I studied this actually a lot for the Borel, and so the answer is basically not always. So you need to restrict to a suitably nice locus of the stack of L parameters. But if you impose the condition that, like, say it's the eigensheaf attached to a parameter phi n, and then you compose this with the adjoint representation on the unipotent radical, let's say I took the contragradient here, then if both of these things are 0, then what you're saying is true.
So under this condition, then.
Yeah. And so actually when phi is a torus, this will just recover the generic condition that appears in Cariani and Scholze. This is actually the mechanism by which we prove torsion band shape.
What is a torus?
If M is a torus, then this will be equivalent to this generic condition that appears in Cariani and Scholze. Yeah, I don't have any time to talk about this, but there's a third object hiding in the background here called a Drinfeld compactification. And this Galois homology group controls the difference between that Drinfeld compactification and this. And that Drinfeld compactification will have this property that it sends eigensheaves to eigensheaves. But yeah, this is all very technical.
It's also a version of B for constant terms. We show that CT preserves ULA's no condition and compacts with this asterisk.
Yeah, well, okay. I originally I was just going to talk about the fact that ISP preserves ULA objects. So, yeah, I mean, there's lots more finiteness theorems you can state, but there's a lot of redundancy between them too. So really, sort of the key point is that it preserves compact and ULA, and that you have this isomorphism here, and all the rest is just sort of formal.
One more question, maybe? If you have a basic, so instead of doing one M, you do some basic M, do you get a similar picture?
Yeah, right. If you took any, if you were to take a basic M, would I get a similar picture as this example? And the answer is yes, but you would then have to talk about varying inner forms and so on. So in my paper with analogy, we did this all very carefully. So you can just take a look at that.
But it gets settled if the image in B of G is not basic.
Well, yeah, it gets a little bit subtle because it's going to be supported on a non-basic Harden-Rosen strata. In fact, the ones where that's true is basically the ones where this inner form will have a parabolic.